Welcome today to Arup Sir's coaching classes of chemistry. Today we will be learning a very interesting topic which aggregates the formation of covalent bond and which is related to the valence bond theory of bond formation. The topic is hybridization. You see, the topic is hybridization. Now guys, you see, every system or everything in our nature as well as in artificial arenas, all systems tries to attain maximum stability. In case of atoms, this is also true, and all the atoms try to attain maximum stability. So to attain maximum stability, which is also the fundamental characteristic of nature, the atom undergoes chemical bonding with each other. That is, they combine with each other. And they combine in such a way that the attractive interaction between the atoms must be a maximum, so that the stability of the system becomes maximum. During the combination of an atom, two different orbitals of atoms, two different orbitals or two different atoms overlaps with each other, so that the electron density between these two nucleus becomes maximum. But during this combination, since the atomic orbitals are quite small, quite less diffused, the extent or the degree of overlap, that is what we call overlap integral, it is quite low. Therefore, whenever the atom combines with each other, they, for making the bond maximum strong, want to overlap with a large area of the orbital. Therefore, during combination, all the atomic orbitals, the valence shell orbitals rather, intermixes with each other to form same number of totally new orbitals containing same energy. And this intermixing process or this phenomenon is called hybridization. So therefore, hybridization may be defined as the phenomenon of intermixing of degenerate or nearly degenerate orbitals of the valence shell of an atom during bond formation to give rise to same number of orbitals of same energy and of bigger size. Okay? I repeat again, the phenomenon of intermixing of degenerate or nearly degenerate orbitals of the valence shell of an atom during bond formation to give rise to same number of orbitals of same energy and of bigger size is called hybridization. I repeat the term degenerate. Degeneracy means containing same energy. Therefore, degenerate or nearly degenerate orbital means orbitals of the valence shells of atoms which contains same energy or nearly same energy. So guys, there are some important points regarding this hybridization procedure. First of all, hybrid orbitals can only form sigma bond. Hybrid orbitals can only form sigma bond and can contain lone pair of electrons. They cannot form pi bonds. Number two, when there are more than one bonds between two atoms, then one will be sigma and the others are pi bonds. For example, in C double bond C, you see there, C double bond C, there are two covalent bonds, out of which one is sigma and the other is pi. Out of C triple bond C, there are triple bonds between two atoms, three covalent bonds between two atoms, out of which one is sigma and the other two are pi bonds. In nitrogen molecule N triple bond N, one is sigma bond and the other two are pi bonds. Similarly, in oxygen atom O double bond O, oxygen molecule O double bond O, one is sigma bond and the other is pi bond. So, number 3, number of sigma bonds around an atom is equal to number of hybrid orbitals is equal to number of pure atomic orbitals, out of which one will be s and maximum 3 may be p, and the rest of all are p orbitals. So I repeat again, number of sigma bonds around an atom will be equal to the number of hybrid orbitals, which in turn will be equal to number of pure atomic orbitals, out of which one will be s orbital, and the 3 maximum can be p orbitals, and the rest of all will be d orbitals. And in case of molecular formula of inorganic molecules which are unknown to us, we may take the help of a formula. H equals to half into V plus M minus C plus A. H equals to half into V plus M minus C plus A, where H is the number of hybrid orbitals, V is the number of valence electrons, in the central atom. M is the number of monovalent atoms attached to the central atom. C is the number of positive charges, and A is the number of negative charges. So, by learning up to this, we could ascertain the state of hybridization of different molecules. But before that, I want to tell you about the hybridization state and the structure or geometry of the molecule. You see, when one s and one p orbital combines with each other, it gives rise to 2 sp hybrid orbitals, and the structure or geometry is linear, like this, and the ideal bond angle is 180 degree. When one s and 2 p orbitals combines or intermixes with each other, they produce 3 hybrid orbitals of same energy, and this is called sp2 hybrid orbitals. And the geometry of the molecule is planar trigonal or trigonal planar. When 4 atomic orbitals, 1 s and 3 p orbitals, intermixes with each other, it gives rise to 4 sp3 hybrid orbitals, and the geometry of the molecule becomes tetrahedral, and the ideal bond angle is 109.5 degree. When 5 atomic orbitals, that is 1 s orbital, 3 p orbitals and 1 number of d orbitals, intermixes with each other, it gives rise to 5 equivalent sp3d hybrid orbitals, and the geometry of the molecule becomes trigonal bipyramidal or TBP, and the structure is given here. You see, these bonds vertically situated are called axial bonds, and the 3 bonds in the plane of the triangle is called the equatorial bond. The bond angle between equatorial and axial bonds is 90 degree, and the bond angle between the equatorial bonds is 120 degree. And now, when 1 s, 3 p and 2 d orbitals intermixes with each other, 6 hybrid orbital results, and this is called sp3d2 hybridization, and the structure of the molecule becomes octahedral with all the axial and equatorial bond angles 90 degree. Now, when 7 atomic orbitals, 1 s orbital, 3 p orbitals and 2 d orbitals intermixes with each other, they give rise to 7 equivalent orbitals, sp3d3 hybridized, and the structure may be pentagonal bipyramidal or capped octahedron or distorted octahedron. The picture is like this. You see a pentagon and 2 axial bonds above and below, and the bond angle between axial and equatorial bonds are all 90 degree. And last of all, there is a special type of hybridization called ds2 hybridization, where 1 d orbital, 1 s orbital and 2 p orbital intermixes to give rise to 4 equivalent dsp2 hybrid orbitals, and the geometry of the molecule or structure of the molecule becomes square planar with all the bond angles 90 degree. Now we will learn the structure, especially what pentagonal bipyramidal and capped or distorted octahedron is. In IF7, that is iodine heptafluoride, there are 7 IF bonds which are situated at the vertices of a pentagonal bipyramid. But in xenon hexafluoride, you see, xenon has 8 valence electrons, and we calculate from each fluorine atom 1 electron. So there are total of 14 electrons, that is 7 pairs of electrons, out of which 6 pairs are bonded, and there is one lone pair which comes out from the middle of the octahedron. That's why the structure is no more an octahedron. It becomes slightly distorted, and that's why it is called distorted or cap octahedron also. To explain you what we have learned till now by certain examples. You see, the molecule methane CH4 it is evident that there are single bonds, 4 single bonds around the carbon atom. Single bonds means always a covalent bond which is sigma bond. So there are 4 sigma bonds around this carbon atom. As we know that the number of sigma bonds equals to number of hybrid orbitals, we can say that carbon possesses 4 hybrid orbitals around it. And since the number of hybrid orbitals equals to the number of pure atomic orbitals, so we could say that to form these 4 hybrid orbitals, 4 atomic orbitals intermixes with each other, out of which 1 is s and maximum 3 remaining are p orbitals. Therefore, in methane, the carbon atom is sp3 hybridized. Again, you see, in ethylene, you see this carbon atom. Around this carbon atom there are 1 sigma bond, 2 sigma bond, and out of these 2 bonds, 1 is sigma bond. So out of these 4 bonds, 3 are sigma bonds. We have already said that if there are multiple bonds between 2 atoms, then 1 will be sigma and others are pi. Therefore, out of double bond, 1 is sigma bond, and this is 1 sigma bond, and this is another sigma bond. So total, around this carbon atom there are 3 sigma bonds. So there are 3 hybrid orbitals, 3 atomic orbitals, 1 s, and the remaining 2 are p. Therefore, this carbon is sp2 hybridized. Similarly, this carbon is also sp2 hybridized. Again, you see another compound, carbon dioxide, CO2, C double bond O, double bond O. Now see, this carbon atom has 2 sigma bonds around it. Out of this double bond, 1 is sigma. Out of this double bond, 1 is sigma. 2 sigma bonds means 2 hybrid orbitals. Therefore, 2 atomic orbitals, out of which 1 is s and the other is p. Therefore, this carbon atom is sp hybridized with a bond angle of 180 degree, and the geometry of the molecule is linear. And in this case, in the previous case, in methane, it is sp3 hybridized with an ACH bond angle of 109.5 degree, and the geometry is tetrahedral. And in ethylene molecule, the carbon is sp2 hybridized with the bond angles of ideal bond angles of 120 degree, and the structure is trigonal bipyramidal. Trigonal, planar trigonal or trigonal planar. Okay, there are 2 triangles. You see that. Now, you see the structure of allene. Allene. Now, this carbon atom possesses 1, 2, and out of these 2, 1. 1, 2, 3. 3 sigma bonds. So there are 3 hybrid orbitals, 3 atomic orbitals, out of which 1 s and the other 2 are p orbitals. So this is sp2 hybridized. sp2 hybridized. This carbon possesses 1, 2 sigma bonds. So it possesses 2 hybrid orbitals. So 2 atomic orbitals are there, and out of which 1 is s and the other is p. So this carbon is sp hybridized. On the other hand, this carbon is also similarly with the first one sp2 hybridized. So this angle is 180 degree, this angle is 120 degree, and this angle is also 120 degree, this angle is also 120 degree, this angle is also 120 degree. Okay. Now you see another molecule CH3 CN. You see this carbon, around this carbon there are 1 and out of triple bond 1, 2 sigma bonds. So there are 2 hybrid orbitals. So 2 atomic orbitals are there undergoing intermixing. So out of 2 atomic orbitals, one is S and the other is p orbital. So this carbon is sp hybridized. But on the other hand, in this one there are 1, 2, 3 and 4 sigma bonds. So 4 hybrid orbitals are there around this carbon atom, which means that this carbon atom, in this carbon atom, the valence shell orbitals, out of the valence shell orbitals, 1 s and 3 p orbitals undergoes intermixing. So this carbon is sp3 hybridized. So this way we can find out the state of hybridization of organic molecules, or the molecules, the structure of which is known. I am giving the last one example once more of propene, CH3 CH2. Okay. Now this carbon atom possesses 1, 2, 3 sigma bonds. So it possesses 3 hybrid orbitals, 3 atomic orbitals, out of which one is S and the other 2p, and therefore it is sp2 hybridized. And in this case you see there are 1, 2 and 3 sigma bonds. So there are 3 atomic hybrid orbitals. So 3 atomic orbitals are present. So out of which one is S and the other 2 are p. Therefore this carbon is also sp2 hybridized. But in this case, in this carbon atom there are 1, 2, 3, 4 sigma bonds. So there are 4 hybrid orbitals, out of which, so 4 atomic orbitals are also there, out of which one is S and the other 3 are p orbitals. So this carbon is sp3 hybridized. We will be learning about finding out the state of hybridization of the central atom of inorganic molecules. So here we have to apply the formula H equals to half into V plus M minus C plus A. Now if you see this ammonia molecule NH3, the central atom is nitrogen. Nitrogen has how many? 5 electron in its valence shell. And hydrogen is monovalent atom, therefore number of monovalent atom is 3. There is no positive or negative charge, that is C equals to 0 and A equals to 0. Therefore number of hybrid orbitals equals to half into 5 plus 3 minus 0 plus 0, which turns out to be 4. Therefore around nitrogen there are 4 hybrid orbitals. So there are 4 atomic orbitals taking part in intermixing. So out of which one is S and the other 3 are p orbitals. So here in ammonia the nitrogen atom is sp3 hybridized and the geometry will be tetrahedral. Geometry will be tetrahedral. There is a difference between shape and geometry. I am today learning, or I am today teaching you how to find out the geometry of the molecule and not the shape. You see another molecule PCl5, phosphorus pentachloride. Now phosphorus has V, valence shell electrons. Number of valence electrons in phosphorus is 5. And number of monovalent atoms stored in his chlorine atoms are monovalent. Therefore there are 5 monovalent atoms. So the formula will be half into 5 plus 5 minus 0 plus 0. There are no positive or negative charges. Therefore the number of hybrid orbitals equals to 5. Since the number of hybrid orbitals equals to 5, therefore there are 5 atomic orbitals undergoing intermixing, out of which one is s orbital, maximum 3 is p orbitals, and the other is d orbital. So here the phosphorus atom is sp3 dehybridized. So the structure is TBP, trigonal bipyramidal, like this. You see the structure is TBP, phosphorus Cl, Cl, Cl. There are two axial PCl bonds. The structures are like this, trigonal bipyramidal. and you see that the axial and equilateral bond angle is 90 degree, but equilateral bond angles are 120 degree. You all see if you join the vertices with imaginary line, you would get a pyramid above and you would also get a pyramid below. So this structure is called trigonal bipyramidal. In case of BCl3, H equals 2, that is number of hybrid orbital equals to half into boron possesses 3 electrons in its outermost shell. Therefore, V equals to 3 plus there are 3 monovalent atoms, chlorine 3. There are no positive charge or no negative charge. So there are 3 hybrid orbitals around boron atom. So 3 atomic orbitals undergone intermixing. So out of which one is free and the other 2 are p orbitals. So here the boron atom is sp2 hybridized and the structure is planar trigonal or triangular. Like this, P, Cl, 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 and all bond angles are 120 degree. Okay. Now we should see another structure. SF6 sulfur hexafluoride. Here H equals to sulfur half into sulfur possesses 6 electrons in its valence shell. So 6 plus there are 6 monovalent atoms attached to sulfur atom. 6. There are no positive charge or no negative charge. So the number of hybrid orbitals around sulfur is 6. So 6 atomic orbitals intermixes, out of which one is s orbital and the other maximum 3 is p orbital and the other 2 are d orbitals. So here the sulfur atom is sp3 d2 hybridized and the structure will be octahedral. Octahedral, you see. And all the equilateral axial bond angles are 90 degree and the equilateral bond angles are also 90 degree. Okay? Now, I'll give example of other molecule. You see water, H2O, oxygen is the central atom, therefore H equals to half into number of valence electron in oxygen atom is 6 plus there are 2 monovalent atoms, 2 hydrogen atoms, 2. There are no positive charges or no negative charges. So the number of hybrid orbitals is 4. So there are 4 atomic orbitals combining with each other, out of which one is s and other 3 are p orbitals. So here the oxygen atom is sp3 hybridized. Now IF7, iodine heptafluoride. Iodine being a halogen atom possesses 7 valence electrons. So number of hybrid orbital H equals to half into 7 plus there are 7 monovalent fluorine atoms attached to the iodine atom. 7 minus 0 plus 0, which turns out to be 7. So there are 7 hybrid orbitals, out of which the 7 atomic orbital intermixes with each other. So there are sp3 d3 hybridized. So iodine atom is sp3 d3 hybridized and the structure is, the geometry is pentagonal bipyramidal. Pentagonal bipyramidal. Okay? There is I atom, 2 axial bonds, 2 axial bonds and other 5 equatorial bonds, fluorine atoms. Okay? This is the structure of iodine heptafluoride. So guys, it is clear to you how we could find the hybridization state or how we could assign the state of hybridization in the set of the central atom in a molecule with known structure or with unknown structure. I think you got it and you learned it. It is the most easy way to find out the state of hybridization of the central atom in a molecule. So for today, bye, and we'll come with new topic in the next session.